The southern hemisphere of the Sun is doing something it should not be doing during this phase of the solar cycle, and approximately 1.2 billion people across the high latitudes of the northern hemisphere are about to spend the next 18 months living downstream of that anomaly without knowing they are doing it. They are not locked in by geography. They are locked in by infrastructure, by the wiring of every modern country between 40 degrees and 70 degrees of latitude, by the long conductive lines of power transmission, by the cellular timing signals that synchronize stock exchanges in Frankfurt and food deliveries in Toronto and dialysis machines in Helsinki, by the satellites overhead that they cannot see and do not think about, by the assumption, never tested in the era of continental electrification, that the Sun will continue to behave the way it has behaved for the 70 years of organized space weather monitoring. That assumption is now in question. A team of scientists published a paper this year in the Journal of Geophysical Research Space Physics. The lead author is Victor Manuel Velasco Herrera. The paper analyzed nearly 50 years of satellite observations of solar soft X-ray emissions, and the prediction it produced should be the most discussed scientific finding of 2026, and it is not. It is buried. It is 6 paragraphs in a single Forbes article that ran on May 24. It is a press release on a university server. It is a technical paper that almost nobody outside the heliophysics community has actually read. The paper says this: the years 2026 and 2027 represent a high-risk window for a class of solar eruptions so powerful that the existing alphabet of solar flare classifications does not have a letter for it. The researchers had to invent one. They call them S-class flares. The S stands for Superflare. The threshold is X10, 10 times the intensity of the lower boundary of an X-class flare, which is itself already the most powerful classification we had a name for before this year. Anything above X10 had no formal label. There were so few of them in the instrumental record that nobody needed one. That is changing. The Sun has been showing us things during this solar cycle that the standard models did not predict. In May of 2024, scientists detected 2 flares on the far side of the Sun that were estimated at X11, 1, and X16, 5, both above the S-class threshold. Both pointed away from Earth by the rotational geometry that happened to favor us in that particular 2-week window. On February 1 of this year, an active region designated 4366 produced an X8-3 flare, the largest of 2026 so far, with another 20-something significant flares from the same region within 48 hours. And as of this week in May of 2026, there are fiery sunspot regions building on the far side of the Sun, currently invisible to direct observation, that are rotating into Earth-facing geometry within the next several days. This is the framing the briefing will work through tonight. The Sun is in a state. The state is anomalous. The state is producing a category of event that the public has no name for. The infrastructure has no defense against, and the forecasting system has no ability to predict in advance. The question is not whether a superflare is possible. The question is whether one is currently building inside the magnetic geometry of an active region we are not yet looking at on a Sun that has just been told by its most recent paper that it is statistically overdue. If this is your first time at a Crisis Horizon Labs briefing, the format is straightforward. We do not chase headlines. We track systems. The kind of systems that hide in technical journals and government bulletins until they collide with the ordinary world, and the ordinary world finds out it was never as separate from them as it thought. If that work matters to you, the subscribe button keeps the briefings coming. The comments below are where this audience does its best thinking. Drop your location and your local time as you read this. We want to see the map of where this signal is reaching. And tell us, honestly, whether you have ever considered solar weather a real category of personal risk. Most people have not. That is part of the problem we are about to walk through. Now, let us get into it. Number. Part 1. The Anomaly. The Velasco Herrera paper is not a press release. It is a peer-reviewed study built on 49 years of soft X-ray observations from the family of geostationary operational environmental satellites operated jointly by the National Oceanic and Atmospheric Administration and the National Aeronautics and Space Administration. The dataset begins in 1976. It contains every recorded X-class flare since instrumentation became continuous. It contains the energy levels, the timing, the heliographic latitude of each event, and the relationship of each event to the 11-year sunspot cycle that the sun has been running, more or less, since modern observation began. The researchers did something that solar physics has historically struggled to do. They stopped trying to predict the next individual flare. The literature has been trying to predict individual flares for 50 years, and the skill remains poor. 24-hour forecasts have meaningful but limited accuracy. 48-hour forecasts have less. Beyond 72 hours, the predictive value of probabilistic flare forecasting drops toward the level of climatological base rates. The sun does not announce its decisions far in advance. The magnetic reconnection that drives a flare is a threshold phenomenon, sensitive to small-scale topology that current instruments cannot resolve. So the team changed the question. Instead of asking when, they asked where, and during which windows. They looked for repeating patterns across half a century of solar behavior, and they found two. The first is a cycle of approximately 1.7 years. The second is a cycle of approximately 7 years. Both periodicities have been noted before in various forms in solar physics literature. What this paper did was track how they overlap, where the troughs of one cycle align with the peaks of another, where two cycles constructively interfere. And in those overlapping zones, they identified time windows during which the probability of an S-class flare, an eruption above X10, is significantly enhanced relative to baseline. The next such window opens during 2026 and remains active through 2027. The probability is asymmetric. It is concentrated in the southern hemisphere of the Sunday. Specifically, the southern heliographic mid-latitudes, where soft X-ray emissions have been clustering during the developing phase of the current cycle in ways the standard active latitude migration model does not fully predict. This is the anomaly. The current solar cycle, designated Cycle 25, peaked in October of 2024, according to the official assessment of the Solar Cycle 25 Prediction Panel. By the standard textbook picture, Cycle 25 should be in its declining phase now. Solar activity should be waning. The probability of major flare events should be dropping month by month as the sun heads toward the next minimum around 2030. That picture is not what we are observing. Cycle 25 was forecast, prior to its onset in 2019, to be a weak cycle. The official prediction was that it would resemble Cycle 24, which was itself the weakest cycle in roughly a century. The predictions were specific. They were published. They were widely cited. And they have, in nearly every measurable respect, been wrong. Cycle 25 has produced more sunspots than predicted. It has produced more X-class flares than predicted. It has produced the strongest geomagnetic storm since 2003, which arrived in May of 2024 and reached G5 status, the highest level on the operational scale. It has produced significant flare activity during what was supposed to be its rising phase, during what was supposed to be its peak, and now during what is supposed to be its declining phase. The decline, if it is happening at all, is happening more slowly and at a higher baseline than the original forecast assumed. And the Velasco-Herrera paper is telling us, in technical and carefully hedged language, that the magnetic geometry of this cycle is not finished. That Cycle 25's magnetic field still possesses sufficient strength and complex topology to generate eruptions in the S-class range. That the high-risk window is not behind us. It is just opening. Keep that thought. We are going to need it. The mechanism behind the 1.7-year and 7-year cycles is not fully understood. The paper is honest about this. They identify the periodicities statistically without claiming to know the physical drivers. The 7-year cycle may be related to torsional oscillations in the solar interior, the rivers of differential rotation that flow at slightly different speeds through the layers beneath the visible surface. The 1.7-year cycle may be tied to a quasi-biennial oscillation that has been observed in various solar parameters for several decades without a confirmed underlying mechanism. What the paper documents is that the overlap of these two cycles is statistically associated with elevated S-class flare probability, that the next overlap window is now, and that the southern solar hemisphere is the predicted preferential zone. There is another piece of evidence we have not yet woven into this picture, and it is important enough that we need to bring it in now, because it changes the prior probability against which the Velasco-Herrera prediction has to be read. In December of 2024, a team led by Valery Vasiliev published a paper in the journal Science. The team used data from the Kepler Space Telescope, which between 2009 and 2013 conducted nearly continuous high-cadence photometry of approximately 150,000 stars. The team filtered the Kepler sample down to stars that resemble our Sun in mass, age, surface temperature, rotation rate, and metallicity. They ended up with 56,450 Sun-like stars. In that sample, they searched for superflares. They defined a superflare, for the purposes of the study, as an optical flare with energy above 10 to the 34th erg, which is roughly an order of magnitude more energetic than the Carrington event and well within the range that would qualify as S-class on the Velasco-Herrera scale. They found 2,889 superflares on 2,527 of those stars over the 4-year observation window. That is a dense forest of extreme events. When the team normalized the result to per-star per-year occurrence rates, they arrived at an estimate that Sun-like stars produce superflares of this magnitude approximately once per century, once per 100 years, not once per few thousand years as the prior literature had estimated. The earlier estimates had been based on smaller samples and on stars whose sun-likeness was less rigorously screened. The new estimate is based on a much larger and more carefully filtered sample. If our Sun is, in fact, a typical Sun-like star, then by the Vasilyev framework, our Sun should produce a superflare on average about once per century. The last confirmed event in the Miyake class range was the 993 to 994 event, which is roughly 1,033 years ago. By that arithmetic, we are statistically overdue, possibly by an order of magnitude in the time domain. This is the kind of statement that requires careful framing. Statistical overdue is not the same as causally overdue. The Sun does not have a calendar reminder. The fact that the last event was more than a century ago does not mean the next event has to occur tomorrow. Rare events distributed in a Poisson-like fashion across time can produce long gaps and short clusters with no underlying physical change. But the elevated probability that the Vasilyev statistics imply is, when combined with the elevated probability that the Velasco-Herrera framework identifies for the current window, a convergence of two independent pieces of evidence pointing toward the same near-term elevation. Two papers, by different teams, using different methods, with different data sets, arrived at compatible conclusions about the present period. One looked at 50 years of our own Sun's behavior and identified a window. The other looked at 4 years of 56,000 other Sun-like stars and identified a baseline rate. Both are saying that the period we are now in deserves more attention than the period before it. When you look at the actual record of S-class events that has been used to validate this prediction, the data set is small. 5 confirmed extreme events in the last 10,000 years, according to cosmogenic isotope records. Possibly 3 more candidates, depending on how you interpret tree ring and ice core anomalies. The instrumental record contains 0 S-class flares with confirmed Earth impact. The strongest flare ever directly measured was an X28 or larger in November of 2003, the so-called Halloween storms event. And even that estimate is uncertain because the geostationary operational environmental satellite's X-ray sensors saturated during the peak and could not record the actual upper bound. Think about that for a moment. The most powerful flare in 50 years of continuous monitoring saturated the sensors. We do not know how big it actually was. We know it was bigger than what our instruments could measure. That single fact, repeated quietly across the heliophysics literature for the last 20 years, should change how confidently we describe the upper limit of solar behavior. The paper proposes that the Sun is capable of producing flares at energies several times larger than anything in the modern instrumental record. The proposal is based on 3 converging lines of evidence. First, the cosmogenic isotope record of past extreme solar particle events, the spike in radiocarbon and beryllium, 1,0 in chlorine, 3,6 recorded in tree rings and ice cores at specific dates over the past several thousand years. Second, the observation of superflares on Sun-like stars detected by the Kepler Space Telescope, which found that stars of roughly our Sun's mass and age and metallicity produce superflares at a rate of approximately once per century in the surveyed population. Third, the magnetic energetics of cycle 25 itself, which still contain enough stored energy to produce the X11 and X16 events we already observed on the far side in May of 2024. Those 3 lines converge on a picture that the standard model of solar quiescence does not accommodate. The Sun has the energetic capacity. The historical record shows it has used that capacity before. The current cycle is showing the magnetic signatures that the researchers have linked to elevated probability, and the time window has just opened. Let me make one technical clarification before we move forward, because the language around solar flare classification gets confusing fast. The standard scale begins at A class, 10 to the minus 8 watts per square meter of soft X-ray flux measured at the Earth's distance from the Sunday. Each successive letter, B, C, M, X, represents a 10-fold increase in that flux. An X1 flare is 100 times more energetic than an M1 flare. An X10 flare is 10 times more energetic than an X1, which puts it 10,000 times above the A1 baseline. The S-class designation proposed by Velasco Herrera and colleagues extends the scale upward without changing its meaning. An S1 flare would be 10 times more energetic than X10, which means 100,000 times more energetic than A1. The Carrington event of 1,859 is estimated, based on the size of the active region observed visually by Richard Carrington himself and the size of the geomagnetic storm that followed, to have been somewhere in the range of X45 to X80. That places it well within the S-class category that the new paper is now proposing as a formal label. So when we say the Sun is about to produce a superflare, we are not saying it is about to produce something that has never happened before. We are saying it is about to produce something that has not happened during the era of continuous instrumental observation, that has happened repeatedly in the recorded past, and that current research indicates we are statistically positioned to receive again in the next 18 months. The southern hemisphere of the Sun is the suspected source. The window is now. But that is only the first layer of the problem. Number. Part 2. The world beneath. There is a world beneath the headlines that runs on electricity. Not just the obvious electricity of lights and refrigerators, the electricity of timing, the electricity of orientation, the electricity of position fixing and currency settlement, and traffic signal cycling, and water treatment plant pump scheduling. The civilization we have built since roughly 1880 has progressively offloaded more and more of its essential coordination functions to electrical systems. The civilization we have built since roughly 1990 has offloaded those electrical systems to the space-based infrastructure that orbits above us. Both layers are vulnerable to a solar superflare in different ways and on different timescales. To understand the actual nature of the threat the next 18 months may bring, you have to understand both layers, because the failures cascade between them. Start with the ground. The electrical grid of any developed country is, in its physical reality, an enormous antenna. Long conductive wires running across thousands of kilometers of landscape, connected together in continental-scale networks, with high-voltage transformers at every major node converting power between transmission voltages and distribution voltages. The transformers are the bottleneck. They are large, they are expensive, they are custom-built for specific grid configurations. The lead time on a new extra high-voltage transformer ranges from 12 to 20 months depending on the manufacturer, the specifications, and the supply chain. And the existing global production capacity, all manufacturers combined, can produce perhaps a few dozen of them per year for the entire world. When a coronal mass ejection arrives at Earth, the geomagnetic disturbance it produces drives fluctuating electrical currents through the upper atmosphere. Those fluctuating currents, through the principle of electromagnetic induction, induce secondary currents in any large conductor at ground level. The conductors most vulnerable to this induction are long, high-voltage transmission lines and the transformers at their endpoints. The induced currents are quasi-direct, slow-varying compared to the alternating current the grid is designed to handle, and they push transformers into magnetic saturation, where the iron core stops responding linearly and starts dumping waste heat into the windings. Transformers that saturate during a severe geomagnetic storm can overheat, melt insulation, fail catastrophically, and require complete replacement. This is not theoretical. It has happened. In March of 1989, a coronal mass ejection arrived at Earth and triggered a geomagnetic storm that collapsed the Hydro-Quebec power grid in approximately 90 seconds. 6 million people lost electricity in the middle of a Canadian winter. The blackout lasted 9 hours. One transformer at the Salem nuclear power plant in New Jersey was permanently damaged by the same storm and required replacement. In October of 2003, the Halloween storms damaged transformers in South Africa, far enough from the magnetic pole that the local utilities had assumed they were safe from geomagnetically induced currents. 12 transformers in the South African grid had to be taken out of service. The country experienced rolling blackouts for months as the system rebalanced. In May of 2024, the G5 geomagnetic storm produced auroras visible as far south as Puerto Rico. No major grid components failed, but high-voltage operators across multiple continents reported significant geomagnetically induced current activity. Margin was eaten. Headroom was used. The storm was, by historical standards, a near miss in technological terms. It happened to occur during a season and time of day and grid loading state that did not stress the most vulnerable nodes. The next one may not. Lloyd's of London, working with the firm Atmospheric and Environmental Research, published a risk assessment in 2013 that modeled what would happen if a Carrington-class event struck the present-day North American grid. The model is specific. Between 20 and 40 million Americans would lose power. The duration of the outage would depend on how many extra high-voltage transformers failed and how quickly replacements could be manufactured and shipped and installed. The low estimate is 16 days. The high estimate is 1 to 2 years. The economic cost estimate for the United States alone is between $600 billion and $2.6 trillion. The upper end of that range is the figure that tends to travel. It is also the figure that is probably closer to the truth, because the 2013 model was built before the United States grid added the dependencies it has today. Cloud computing data centers that require continuous power and water cooling. Battery electric vehicle charging networks that draw at megawatt scales. Renewable energy generation that depends on grid frequency stability to remain synchronized. The North American grid of 2026 is more interconnected, more software dependent, and arguably more fragile than the grid Lloyd's modeled 13 years ago, and it is one of the more resilient grids on Earth. Europe's grid is comparable in some respects, and more fragile in others, particularly in its dependence on long-distance imports from the East. The grid of India is significantly more vulnerable to induced current events because of its lower headroom and aging transformer fleet. The grids of sub-Saharan Africa and Southeast Asia are still in growth phases that have not been designed with extreme space weather as a primary threat. The picture, taken globally, is that the world's electrical infrastructure has been built during an unusually quiet period of solar history. The first 140 years of widespread electrification, from roughly 1880 to today, have not contained a Carrington-class event with Earth impact. The infrastructure has, in effect, never been tested under conditions that the historical record says occur on the timescale of a century or two. Now layer the Second World on top of that. The space-based infrastructure that modern civilization runs on consists of approximately 11,000 active satellites in orbit around the Earth as of the start of 2026, with the number rising rapidly. The largest single constellation is Starlink, with more than 6,500 satellites and growing. Other significant constellations include OneWeb, Iridium, the Global Positioning System operated by the United States Space Force, the European Galileo system, the Russian GLONASS system, and the Chinese Beidou system, all of which provide positioning and timing services that the world depends on. There are weather satellites, communications satellites, Earth observation satellites, scientific satellites, and a growing volume of satellite traffic in low Earth orbit between roughly 200 and 1,200 kilometers altitude, where the atmosphere is thin enough to permit orbital flight, but dense enough that any perturbation of its density affects satellite trajectories. That last sentence is the one to pay attention to. The thermosphere, the upper layer of Earth's atmosphere where low-orbit satellites fly, expands when energy is dumped into it. Geomagnetic storms dump energy into it. Solar extreme ultraviolet radiation heats it. During the May 2024 storm, the thermospheric density at altitudes between 200 and 400 kilometers increased by 50 to 125% above pre-storm values. That density increase translates directly into atmospheric drag on satellites. Drag slows them down. Slower satellites drop to lower orbits. Lower orbits encounter denser air. The process accelerates. During the May 2024 G5 storm, one Starlink satellite, designated 2601, fell from an altitude of 276 kilometers to 100 kilometers in less than 2 days. It burned up in the atmosphere on re-entry. It was not alone. Approximately 12 Starlink satellites are documented as having had their orbital lifetime significantly shortened by that single storm. The February 2022 event, which was a much smaller geomagnetic storm, caused 38 Starlink satellites to deorbit prematurely before they ever reached operational altitude. From 2020 to 2024, approximately 1,190 satellites re-entered from very low Earth orbit, and nearly half of them were Starlink. That number is roughly tracking the rising phase of cycle 25. A G5 storm cost about a dozen satellites in 2024. An S-class flare, if it produces a coronal mass ejection of corresponding magnitude, would not cost a dozen. It might cost hundreds. It might cost thousands. The thermosphere does not have a graceful failure mode. It heats. It expands. And every satellite in low Earth orbit experiences correspondingly higher drag for the duration of the event. And that is just the drag effect. The radiation effect is separate. Energetic particles from a major solar event penetrate satellite hulls and induce charge accumulation in electronics, single event upsets in memory chips, and gradual radiation damage to solar panels and sensors. Satellites in geostationary orbit, where most of the high-value communications and weather satellites live at 36,000 kilometers altitude, are outside the protection of Earth's magnetic field for most of each day and are particularly exposed. Hardening helps. Operational procedures help. But there is a class of events large enough to overwhelm hardening, and an S-class flare is in that class. What does it mean for the world that runs on satellites if a fraction of the constellation goes dark? It means global positioning system timing signals become unreliable in regions where redundancy is thin. Financial transaction networks depend on global positioning system timing to coordinate settlements across exchanges. Power grid synchronization depends on it for frequency control. Cellular networks depend on it for cell tower handoffs. Aviation depends on it for precision approach and en route navigation. Maritime depends on it for everything. The interdependencies are not always obvious, and they are not always documented, because the systems grew up gradually, and the assumptions about positioning and timing availability got baked into software architectures over 30 years of continuous service. The world beneath is not just the world below the atmosphere. It is the world below the layer of space-based infrastructure that the world above the atmosphere now requires to function, and both worlds are exposed, on different timescales and through different mechanisms, to the same incoming event. There is a third layer that we should mention before moving on, because it sits between the ground and the satellites, and it is the layer that almost nobody thinks about: the cables. Specifically, the submarine fiber optic cables that carry roughly 95% of all transcontinental data traffic, including financial transactions, internet routing, and government communications. Submarine cables are not, in the strictest sense, vulnerable to geomagnetically induced currents in the way that overhead transmission lines are. The cables themselves are short relative to the wavelengths of geomagnetic disturbance, and they are submerged in seawater that provides a degree of electromagnetic shielding. But the cables are not entirely passive. They contain repeaters at intervals of roughly 50 to 100 kilometers, which boost the optical signal as it degrades over distance. The repeaters are powered through a direct current voltage applied at the cable's landing stations, which can run to thousands of volts across the length of a transoceanic cable. The power feed equipment at landing stations connects to the local power grid. When the grid goes down or experiences significant transients, the power feed equipment can be damaged, and the cable can lose service. During the May 1989 storm, multiple submarine cables across the North Atlantic experienced anomalies, and there were reports of cable system disruptions during the May 2024 storm as well. Although operators have not published detailed post-event analyses, the vulnerability is not the cable itself. The vulnerability is the connection between the cable's power infrastructure and the terrestrial grid that the rest of the world's infrastructure depends on. Take the grid down, and the cables follow within hours or days, depending on the backup power configuration at the landing stations. This matters because the cables are how the financial system breathes. Settlement of cross-border transactions, foreign exchange operations, securities clearing, and the global routing of internet traffic all depend on the cables. The financial system has redundancy. The redundancy is at the protocol level. It is not at the level of physically diverse cable routes operating independent of correlated terrestrial power outages. If the power grid goes down in multiple major financial centers simultaneously, the cables either lose service or transmit data that nobody is able to receive and process. The systemic resilience of the global financial system has not been tested against a coordinated, geographically widespread, multi-week power outage. The contingency plans exist. They have not been exercised at the scale a major space weather event would impose. This is the kind of dependency stacking that the framework gap allows. Each layer of infrastructure was designed against the threats most relevant to that layer. The interactions between layers, the way a grid failure cascades into cable failures, into financial system failures, into food supply failures, are not the responsibility of any single agency or industry. The cascade lives in the gaps between the responsibilities. The gaps are where the next bad thing comes from. Stay with me. The mechanism that connects all of this is where the next layer of the problem lives. Part 3. The machinery. To understand what a solar superflare actually is, mechanically, you have to start at the surface of the sun and work your way backward into the physics that produces it. The picture matters because it explains why prediction is so hard and why the warning window, once we have one, is so short. The sun is a sphere of plasma. Plasma is a state of matter in which atoms have been ionized, stripped of one or more electrons, so that the bulk material consists of charged particles that respond directly to electromagnetic fields. The interior of the sun is plasma. The atmosphere of the sun is plasma. The wind that blows outward from the sun and fills the entire heliosphere is plasma, and plasma, unlike neutral matter, carries magnetic fields with it as it moves. The fields and the plasma are coupled. Where the plasma flows, the fields go. Where the fields are stronger, the plasma is constrained. Inside the sun, the layers do not rotate uniformly. The equator rotates faster than the poles. The outer layers rotate at slightly different speeds than the inner layers. The deeper layers rotate as a rigid body. The combination of these differential rotation patterns winds up the magnetic field over time, twisting field lines around the solar interior, building up structure and complexity that emerges to the surface in the form of sunspots. Sunspots are the visible footprints of magnetic flux tubes that have risen from the deep interior through the convection zone and broken through the photosphere into the corona. The outer atmosphere of the sun, where temperatures reach millions of degrees and the material is so thin that the magnetic field controls almost everything. In the corona above a complex active region, the magnetic field is highly structured. It contains loops of field lines arching above the surface, regions where the field reverses direction over short distances, and configurations where oppositely directed field lines are pressed together by the motion of the plasma below. This is where flares come from. A solar flare is, in its most fundamental physical description, the result of magnetic reconnection. Magnetic reconnection is a process in which two regions of oppositely directed magnetic field press together until the topology of the configuration becomes unstable, abruptly restructure their connectivity. Field lines that previously went one way and another way suddenly merge and reform into new configurations. The reconfiguration releases enormous quantities of magnetic energy in a very short time. Some of that energy goes into the kinetic energy of accelerated particles. Some goes into the bulk heating of plasma. Some goes into electromagnetic radiation across the spectrum from radio waves to gamma rays. Some, in many cases, drives the eruption of a large bubble of magnetized plasma out into the heliosphere, the phenomenon we call a coronal mass ejection. The energy that a flare can release is bounded by the amount of energy stored in the magnetic field of the active region beforehand. That stored energy depends on the size of the active region, the complexity of its magnetic topology, the strength of the field, and the shear of the field, which is a measure of how much the field has been twisted by the differential motions of the plasma below it. The largest sunspot groups can store, in their magnetic configurations, energies up to roughly 10 to the 33rd or 10 to the 34th erg. The Carrington event is estimated to have released roughly 4 to 6 times 10 to the 32nd erg. A superflare in the S-class range would release 10 to the 33rd erg or more. The energy capacity exists. The question is whether the topology of any given active region will cross the reconnection threshold at the right time and in the right direction relative to Earth to produce a major event with Earth impact. That threshold is the problem. Magnetic reconnection is what is called, in the language of nonlinear dynamics, a critical phenomenon. The system can sit near the reconnection threshold for hours or days, exhibiting increasing complexity and increasing stored energy, with no externally visible sign that the configuration is about to fail catastrophically. The transition from the stable, near-threshold state to the eruption state happens on a timescale of seconds to minutes. The actual physical trigger, the small-scale magnetic geometry that crosses the threshold first and initiates the reconnection cascade, occurs at spatial scales smaller than any instrument currently deployed can resolve. This is not a problem that better instruments will solve in the near term. It is a property of the system. The Sun is a near-bifurcation dynamical system. The macroscopic observable quantities, the size and shape and brightness and magnetic field strength of an active region, do not uniquely determine which future state the system will enter. Active regions of similar appearance can flare immediately, flare in a few hours, flare in a few days, or never flare. The reconnection initiation is sensitive to small-scale, sub-resolution magnetic configurations that we cannot see in real time. What this means operationally is that we cannot predict, in the strict sense, when the next major flare will occur. We can only detect it after it begins. The detection happens fast. The first signal from a flare is electromagnetic radiation, X-rays, and extreme ultraviolet, which travels from the Sun at the speed of light. It arrives at Earth orbital distance approximately 8 minutes after the flare initiates. The X-ray sensors aboard the geostationary operational environmental satellites detect the flux increase, and the Space Weather Prediction Center, operated by the National Oceanic and Atmospheric Administration, issues an alert within minutes of detection. The alert reaches grid operators and satellite operators and aviation route managers in something like 10 to 15 minutes total from flare onset. That is the warning. 10 to 15 minutes. What follows that warning, over the next minutes to hours, is the energetic particle component. Protons accelerated to a significant fraction of the speed of light begin arriving at Earth orbital distance. The fastest, highest energy protons from the most powerful events can begin arriving 15 to 20 minutes after flare onset. The bulk of the particle flux from a large solar energetic particle event takes 1 to several hours to reach peak intensity. The elevated flux can persist for many hours, sometimes more than a day. The particle flux is what damages satellites. It is what threatens astronauts in space. It is what produces the radio blackouts that disrupt high-frequency communication. It is what we have to be in shelter from, if we are an astronaut, or what our hardware has to be protected against, if we are a satellite operator. The particle event is fast, but not instantaneous. And then comes the third component, the slow one. The coronal mass ejection. If the flare drives a major mass eruption, a cloud of magnetized plasma carrying millions of tons of solar material at speeds of several hundred to several thousand kilometers per second, that cloud takes 1 to 3 days to reach Earth, depending on its speed. Coronagraphs aboard the Solar and Heliospheric Observatory and the Solar Terrestrial Relations Observatory can image the cloud after it leaves the Sun and track its trajectory. The arrival time at Earth can be predicted within a window of plus or minus several hours. That gives ground-based infrastructure operators a meaningful warning window, 24 to 72 hours, to prepare for the geomagnetic storm that arrives when the cloud interacts with Earth's magnetosphere. So the warning structure is staged. 8 to 15 minutes for radio blackouts and immediate radiation, 15 minutes to several hours for the particle flux, 1 to 3 days for the geomagnetic storm. But here's the thing about an S-class flare. The staging may collapse. Some of the most extreme flares observed on Sun-like stars by the Kepler Space Telescope produced particle events with arrival times much faster than the standard model predicts. The fastest solar energetic particles ever recorded, from the so-called ground-level enhancement events that produce measurable increases in cosmic ray flux at the surface of the Earth, arrived within 10 to 20 minutes of the parent flare. There have been a handful of these events recorded directly. The most extreme of them, in cosmogenic isotope evidence, suggest fluxes that would deliver radiation doses on aircraft routes and at high altitude in minutes rather than hours. The 2013 paper by Adrian Mellett and Brian Thomas modeled the atmospheric chemistry consequences of the 774 AD Miyake event, which is the largest documented solar particle event in the last 10,000 years. The model suggests that the event produced sufficient nitrogen oxides in the upper atmosphere to measurably deplete the ozone layer for years afterward, and that biological doses at high latitude during the event would have been roughly 2 to 3 times the annual background dose, delivered in a single window of hours to days. That is the kind of event we are talking about when we say superflare. Not a stronger version of what May 2024 brought, a qualitatively different category of event, one whose timing structure may not give us the staging of warnings that operational forecasting currently relies on. One whose particle component may be faster, sharper, and harder to shelter from than anything in the modern record. The forecasting gap matters here. The 2031 launch of the European Space Agency's Vigil mission will give us a side view of the Sun from the L5 Lagrange point, allowing us to see active regions and coronal mass ejections that are currently obscured from Earth's direct view because they are on the far side or near the limb. Vigil is the most significant operational improvement to space weather monitoring in decades. It will help. It is not currently operational. We are working with what we have. And what we have today is the detection of an event after it has started, with a warning window that is short and maybe shorter than expected for the largest class of events. There is one more piece of the machinery worth understanding before we move on, and it is the piece that has been quietly studied for the last 15 years by a small community of researchers working on what are called ground-level enhancement events. A ground-level enhancement is a solar particle event so energetic that some of the incoming protons reach energies above 500 million electron volts, which is the threshold above which the particles can produce secondary cascades in the atmosphere that propagate all the way down to the surface of the Earth and produce measurable increases in radiation at sea level. The increase is small compared to natural background and does not pose a direct health risk under normal conditions. What it does pose is an unambiguous signature in the cosmic ray neutron monitor network that has been operating, in various configurations, since the International Geophysical year of 1957 to 1958. The neutron monitors record the ground-level radiation, and when a ground-level enhancement occurs, the monitors register a sharp spike that can be precisely timed. Approximately 73 ground-level enhancement events have been recorded since systematic neutron monitor coverage began. The events range in magnitude from barely detectable enhancements of a few percent above background to the largest event in the record, which occurred in February of 1956 and produced enhancements of nearly 5,000% above background at some northern stations. The 1956 event was so large that, by some estimates, it would have delivered a radiation dose of approximately 10 rem to an astronaut who happened to be unshielded in space during the peak of the event, which is roughly 10 times the annual radiation dose limit for occupational exposure. The 1956 event happened during a relatively quiet portion of the solar cycle. It was not associated with the largest flare of the cycle. It was not predicted. It was, in essentially every meaningful way, a surprise. And it is a useful reminder that the relationship between flare class and particle event severity is not as tight as the public framing of solar weather suggests. A modest flare in a favorable acceleration geometry can produce an extreme particle event. A massive flare with poor geometry can produce relatively modest particle effects. The variables that determine the severity of the particle component, including the configuration of the magnetic field, the speed and structure of the coronal mass ejection that often accompanies the flare, and the orientation of the interplanetary magnetic field at the time, are not fully captured by the X-class flare magnitude alone. This is part of what makes operational forecasting so difficult. The single number that summarizes the flare, the X-class designation, is one input into a much higher dimensional system that determines what actually arrives at Earth. The same number can correspond to wildly different consequences depending on the other variables. The forecasting framework that the Velasco-Herrera paper proposes is one of the first systematic attempts to address this complexity at the timescale of windows rather than individual events. It is the right direction. It is also still preliminary. What the historical ground-level enhancement record tells us is that the upper end of solar particle event severity is well above the upper end of what the modern measurement network has had to manage operationally. The 1956 event was measured by relatively crude neutron monitor stations and recovered indirectly through the cosmogenic isotope signature. A 774 class event, if it occurred today, would produce neutron monitor responses several times larger than 1956. The neutron monitor network would record it cleanly. The The biological dose at altitude would be measured directly by the radiation monitors aboard high-altitude aircraft. The signature would be unmistakable. The question is what we would do with the signature in the few hours during which the particle flux remained elevated. The answer, for most categories of operation, is that we would manage it after the fact. Aircraft would be grounded for the duration of the elevated radiation environment. Satellite operations would be safed where possible. Astronaut shelter protocols would be activated. The damage that the event was going to cause would have, in large part, already been initiated by the time the response was operational. The particle event is too fast for response to be more than triage. Now consider the staging of effects for a major event in more detail, because the timing matters when we start talking about cascading consequences. T=0. The flare initiates on the surface of the Sunday. The magnetic reconnection cascade releases its energy. The first photons depart at the speed of light. The plasma begins to be accelerated by the reconnection process and by the shock wave that the eruption drives ahead of itself. The coronal mass ejection, if one occurs, begins to detach from the solar surface. T=approximately 8 minutes. The first X-rays and extreme ultraviolet photons arrive at Earth. The geostationary operational environmental satellite X-ray sensors register the flux. The Space Weather Prediction Center issues an immediate alert. Radio blackouts begin on the sunlit hemisphere of Earth, almost instantly, as the upper ionosphere absorbs the incoming high-frequency radio waves. High-frequency radio communication, which is used by aviation over polar routes, ships at sea, and some emergency services, becomes unreliable. T=approximately 15 to 20 minutes. The fastest protons from the event begin arriving. The flux at geostationary orbit and at high latitudes in low Earth orbit begins to rise. Satellite operators initiate protective protocols. Astronauts, if any are in transit beyond low Earth orbit, begin to shelter. The radiation environment at altitudes above approximately 10 kilometers begins to elevate on polar routes. T=1 to several hours. The bulk of the solar energetic particle flux reaches Earth orbital distance. Peak particle flux is reached. Polar aviation routes are diverted. Some satellites in geostationary orbit experience single-event upsets, anomalies in onboard electronics, and in extreme cases, hardware failures. High-frequency radio remains disrupted across large portions of the planet. The Global Positioning System constellation begins to register elevated noise on its signals as the particle environment affects the receivers. T=1 to 3 days. The coronal mass ejection arrives. The compressed magnetic field of the cloud, on contact with Earth's magnetosphere, drives the geomagnetic storm. Auroras expand toward the equator. Geomagnetically induced currents begin flowing in long conductors at the surface. Power grid operators monitor for transformer saturation. The storm peaks, then declines over the following day or two. T=1 to 7 days after storm peak. Transformer damage, if it has occurred, begins to manifest in service. Some transformers fail immediately. Some fail in the days following, as accumulated thermal damage progresses toward catastrophic failure. Satellites that suffered radiation damage begin to show operational anomalies. Some recover, some do not. The damage assessment becomes clearer. T=1 week to several months. The infrastructure consequences are absorbed. Transformer replacements are ordered. Power restoration proceeds where transformers have been damaged. Satellite operators report losses and begin replacement procurement. Insurance claims begin to be filed. The economic consequences become quantifiable. This is the staging for a Carrington-class event. For an S-class event, the staging compresses on the early end and extends on the back end. The particle component arrives faster and harder. The damage is more widespread. The recovery takes longer because the supply chain for replacement components is finite, and the demand is geographically distributed in ways that exceed the capacity of any single manufacturing region to fulfill quickly. Without a clean name yet, that is the framing this paper keeps coming back to. The Velasco Herrera team gave us a label, S-class, but the label is provisional. The category it describes is a category that we have not lived through in the era of continuous instrumental observation, that we have witnessed only through indirect proxies in tree rings and ice cores, and that we cannot model with the same confidence as smaller events because we have no calibration data from inside it. We know it is coming. We know it is more likely to come during the next 18 months than during any equivalent period in recent decades. We know it may come faster, hit harder, and stage its arrival differently than what our operational infrastructure has been built to absorb. And that is only the machinery. The framework that surrounds the machinery is the next layer, and it is where the situation actually gets worse. Part 4. The nameless thing. There is a category of solar event that exists in the historical record but does not exist in the modern instrumental record. The category has a name that scientists have used informally for 15 years and that the public has almost never heard. The name is Miyake event, and what it represents is, in the most literal sense, the kind of solar storm whose existence we can only verify by looking at tree rings. In 2012, a Japanese researcher named Fusa Miyake published a paper in Nature. She had been analyzing the annual growth rings of Japanese cedar trees, measuring the concentration of radiocarbon, the isotope carbon, 1,4, in each ring. Carbon, 1,4, is produced in the upper atmosphere when high-energy particles interact with atmospheric nitrogen. The production rate depends on the flux of incoming cosmic rays. Most years the flux is roughly constant. Some years it spikes. The spike Miyake found in the tree rings dated to 774 and 775 of the Common Era was so large that it could not be explained by normal variation in galactic cosmic ray flux. It was something between 10 and 20 times the typical year-to-year variation. The spike showed up in tree rings from Japan, from Germany, from Russia, from New Zealand, and from North America. It was global, it was synchronous, and it required an enormous flux of energetic particles to have hit the Earth's atmosphere during a very narrow window. Subsequent work by other groups identified additional cosmogenic markers, beryllium 10 inches ice cores and chlorine 36 inches glacial deposits, with synchronous spikes at the same date. The combination of isotopes provided enough information to constrain the spectrum of the incoming particles. The particles were hard, meaning they were dominated by very high energies, well above 100 million electron volts. The flux was several times anything in the modern instrumental record. The most rigorous estimates put the event at least 5 times stronger than any solar particle event that has been directly measured by satellites since 1976. The 774 to 775 event was not unique. Subsequent searches of the tree ring and ice core record identified additional events, one in 993 to 994, one in 660 BCE, one in 5259 BCE, one in 7176 BCE, one in 12,350 BCE, the largest of all, which was identified from subfossil pine trees recovered from the French Alps and which produced a radiocarbon spike of approximately 3.1% in a single year, the largest known anomaly in the cosmogenic record. 5 confirmed Miyake events, 3 additional candidate events, over the last 10,000 years. That is the rate, roughly 1 event of this class, per 1,200 to 1,500 years on average, with significant clustering in some periods and gaps in others. It is statistically possible to live through several centuries of civilization without experiencing one. It is also statistically possible to experience 2 within a few hundred years, as we did with the 774 and 993 events. The 774 event is now widely accepted to have been solar in origin. The early hypotheses included a nearby supernova, a gamma-ray burst, or a comet collision, but the multi-isotope evidence and the high energy hardness of the particle spectrum points unambiguously to solar energetic particles produced by an extreme solar event. The Sun did this, probably with a flare, probably with an accompanying coronal mass ejection. Probably, by any reasonable energy accounting, in the S-class range that Velasco, Herrera, and colleagues are now formally defining. The Sun has done this before. It has done it within recorded history, even though the records of the day did not understand what they were witnessing. There are accounts in Chinese chronicles of 774 of unusual atmospheric phenomena. There are records in European monastic chronicles of aurora at unusual latitudes. The instrumental signatures are unambiguous. The event happened. The atmosphere recorded it. The trees recorded it. The ice recorded it. Now consider what that event would do to the world we have built since then. The 1859 Carrington event, which is the modern benchmark for solar storm severity, is estimated to have been an X45 to X80 class flare. The 774 Miyake event was, by the cosmogenic estimates, larger. perhaps 5 times larger by particle flux, perhaps an order of magnitude larger in total energy. The Carrington event happened during the early days of telegraph electrification, when total electrical infrastructure on Earth consisted of a few thousand kilometers of telegraph line, no power grid, no electronics, no satellites. The Miyake event would, if it occurred today, encounter 11,000 satellites, a continental grid system in North America and Europe and Asia, billions of consumer electronic devices, and a financial and logistics infrastructure that has spent a century building dependencies on uninterrupted electrical service. There is no historical scenario that maps cleanly to what such an event would do. The Carrington-level scenarios that Lloyd's modeled in 2013 are bounded by the energy of the 1859 event. A Miyake-level event would be substantially worse, not because the warning window would be different, not because the physics of induced currents would be different, but because the magnitude of the disturbance would push the infrastructure further past its tested limits in ways the existing risk models extrapolate poorly. This is the category we have no name for in the operational sense. The Velasco-Herrera paper proposed S-class as a label for flares above X10, but the historical record contains events that may have been substantially above X10, events at X100, X200, or higher. Events whose actual energetic upper bounds we do not know because the instruments saturated then, and because the instruments did not exist for most of the events we have evidence of. The category exists. The category has happened. The category is not on any operational solar weather forecast scale. The category is what the new paper is hinting at when it says cycle 25 still has the magnetic capacity to produce extreme events, and what the historical cosmogenic record is shouting when it shows us the imprint of solar behavior that we have never directly observed. What do you call something that has occurred multiple times in human history, that current science cannot predict, and that current infrastructure has never been built to withstand? You do not call it anything. You hope it does not happen during your shift. That hope is not policy. It is not a plan. It is what we have by default in the absence of anything better. The Miyake events are the part of this story that almost no public discussion of solar weather acknowledges. Conversations about Carrington-level events are now reasonably mainstream. Power utilities are aware. Insurance markets price for them. Government agencies plan for them in their disaster preparedness frameworks. But conversations about Miyake-level events, events at the upper end of what the sun has historically produced rather than the upper end of what we have instrumentally measured, are confined to specialist literature and a small number of researchers who study extreme solar particle events for a living. That is the gap. That is the framework gap. Our public risk consciousness extends to the upper bound of the modern instrumental record. The actual physical upper bound of solar behavior, as documented by cosmogenic proxies, extends substantially beyond that. We have built our infrastructure, our planning, our insurance models, and our public communication around the wrong upper bound. Is this a coincidence or something else? Let me know in the comments. Because if you have read this far, you are the part of the audience that thinks about these things, and your instinct about why the conversation has stayed where it has stayed is probably worth more than another paragraph of mine. Keep that thought. There is one more layer to this, and the layer is not physics. It is sociology. Number. Part 5. The coverage gap. There is a reason this story is not getting the attention it should be getting. The reason is structural. It has to do with where the threat is geographically distributed, who is most exposed, and how news coverage allocates its attention to events whose timing and magnitude are uncertain. The threat from a solar superflare is not geographically uniform. It is latitude-dependent. Geomagnetic induction in power grid transformers is most severe at high magnetic latitudes, where the auroral oval expands during major storms and the gradient of the magnetic field is steepest. The transformers most at risk during a Carrington-class event are in southern Canada, the northern tier of the United States, Scandinavia, the United Kingdom, northern Russia, and the southern tip of South America. The transformers least at risk are in the equatorial regions of the world: India, sub-Saharan Africa, Southeast Asia, the equatorial Pacific. Geomagnetic induction is weaker there. The risk to grid infrastructure is lower. But the risk to satellites is not latitude-dependent in the same way. Satellites are exposed to the particle event globally. The geostationary belt, where most communications and weather satellites live, is at 0 degrees latitude relative to Earth's equator and is exposed to whatever the sun delivers, regardless of where the receiving country is on Earth's surface. The global positioning system constellation, the cellular timing networks, the financial settlement systems, all of these are global infrastructure. A satellite outage affects users at any latitude with the same severity, so the risk picture is geographically split. The grid risk is concentrated in the developed world at high latitudes. The satellite risk is global. And the cascading consequences of the two combined are concentrated wherever the dependencies are most stacked, which is also the developed world. This produces a strange dynamic in the news coverage of solar weather. The countries most exposed to the grid component, North America and Europe and East Asia, are the countries that produce most of the world's English-language news coverage. So when major solar storms occur, the framing centers on what happens to those countries. The May 2024 storm was covered extensively for its auroral displays in the continental United States, for its impact on Starlink, for the elevated geomagnetically induced currents reported by North American grid operators. The framing was, throughout, what happens to us when the sun does this. That framing is not wrong. It is accurate. What it misses, and what the Velasco-Herrera paper makes explicit, is that the southern solar hemisphere is the predicted high-risk source zone for the next S-class events. The southern solar hemisphere is the source. The Earth, regardless of its own hemisphere, is the receiver. The geometry of which Earth latitudes are most affected by a given event depends on the orientation of the magnetic field within the coronal mass ejection, which is determined by complex interactions during the eruption process, and which can produce profoundly different geographic distributions of damage from events of nominally similar energy. The point is not that the northern hemisphere is safer than the southern hemisphere in a population sense. The point is that we have predicted the source. The source is anomalous, and the coverage of that prediction has been almost zero. Compare this to the coverage that other categories of natural disaster receive when scientists publish predictions of elevated risk. A hurricane season prediction from the National Oceanic and Atmospheric Administration generates national news. A volcanic activity warning from the United States Geological Survey generates immediate coverage. An earthquake hazard assessment in the western United States generates ongoing public discussion. A scientific paper predicting an elevated probability of a Carrington-class solar event over an 18-month window generates one Forbes article and a handful of trade publication citations, and then disappears into the noise of daily news. Why is the disparity that wide? Part of it is that solar weather has historically been treated as an exotic threat. The phenomena are physically removed from human experience. Most people have never seen an aurora. Most people do not know what a coronal mass ejection looks like. The threat is invisible by the standards of ordinary perception. It does not produce loud sounds or visible storms or photographable damage in the way that hurricanes and earthquakes and volcanoes do. The intuitive risk channel that humans use to assess danger does not light up for solar weather, even when the actual statistical risk is significant. Part of it is that the threat is probabilistic in a way that resists clean headlines. A hurricane forecast can say, with high confidence, that landfall will occur in a specific region on a specific day. A superflare forecast says, with moderate confidence, that the probability of an extreme event is elevated during a window of months. That is a harder story to tell. It is a harder story to keep telling, week after week, for the duration of the window, when no event has yet occurred. The news cycle does not handle this kind of story well. Part of it is that the consequences are also probabilistic. A direct Earth impact from a major coronal mass ejection requires a specific geometric alignment, a specific orientation of the embedded magnetic field, and a specific timing relative to the susceptibility of the receiving infrastructure. Many large solar events produce no significant Earth impact because they fire in directions away from Earth, or arrive with magnetic field orientations that the Earth's magnetosphere can easily deflect. The May 2024 storm was a notable event precisely because all of the geometric and timing factors aligned to produce a significant impact. Most events do not align that way. So the public encounters solar weather coverage mostly through the lens of pretty aurora photos and not through the lens of operational threat. The threat assessment exists in the technical literature. It does not translate cleanly into the public conversation. There is one more dimension to the coverage gap that deserves explicit attention, because it relates directly to the geographic asymmetry that the Velasco-Herrera paper has identified. The southern solar hemisphere being the source zone for the predicted S-class events is, from the perspective of communicating the risk, a particularly inconvenient fact. Most of the world's space weather communication infrastructure is built around northern hemisphere observations of the Sunday. Most of the news outlets that cover space weather are headquartered in the northern hemisphere. Most of the population that consumes space weather news lives in the northern hemisphere. The southern solar hemisphere is not the southern terrestrial hemisphere. The geometry is independent. Active regions on the southern half of the Sun can produce coronal mass ejections that arrive at Earth and impact the northern hemisphere of our planet, depending on the orientation of the ejection and the magnetic configuration of the cloud. The physical phenomenon is global at Earth, even though the source is hemispheric on the Sunday. But the framing of the prediction, the way the paper describes the source region, creates a translation problem for the news coverage. The natural framing is to say that the southern solar hemisphere is the predicted source. That framing does not carry the urgency that a similar prediction about a hurricane breeding ground or an active seismic zone would carry. The Sun is not a place that the audience visualizes geographically. The southern solar hemisphere is, for almost every audience, a phrase without a location associated with it. This is part of why the story has not broken through. The geographic frame that natural disaster reporting uses to communicate urgency does not function when the geographic source is on a body that the audience does not visualize. The asymmetry of impact is, however, very much terrestrial, and it is concentrated where the audience does live. The mismatch between where the threat is described as being located and where its impact will actually land is, in some ways, the central communication problem of solar weather as a category. And there is another factor, and this one is harder to name without sounding cynical. The communities most exposed to the grid component of a major solar event are wealthy enough that the consequences of being wrong about the threat are absorbed by the political and economic system rather than expressed visibly in immediate hardship. If a coronal mass ejection takes down 10 extra high-voltage transformers in the northeastern United States in late winter, the immediate visible impact would be widespread power outages, but the response infrastructure exists, the population is relatively well-resourced, and the political system would mobilize to manage the crisis. The hardship would be real. The hardship would not look like the kind of hardship that produces sustained international news coverage. There would be no images of refugees crossing borders. There would be no famine. There would be a quieter, slower kind of damage. Frozen pipes, spoiled food, elderly people dying from cold or from medical equipment failure. Businesses closing, markets disrupted. The shape of the suffering would be a shape that does not produce iconic photographs. Compare that to the way a major hurricane or a major earthquake produces images and stories that hold international attention for weeks. The visibility differential matters. Solar events, even severe ones, produce a kind of damage that resists visualization. The aurora is photogenic. The transformer fire in a Virginia substation at 3 in the morning is not. This is part of what we mean when we talk about the coverage gap. The story does not photograph well. The story does not fit clean narratives. The story exists in technical journals and in the quiet calculations of insurance underwriters and in the conversations of grid operators who plan for events they hope they will never have to manage. The story does not live in the daily conversation, even though the probability assessment of the next 18 months has just shifted in a way that should command attention. Crisis Horizon Labs exists, in part, to be the place that closes coverage gaps. That is the editorial mission. That is why we are spending an hour and 20 minutes on a Forbes article that almost nobody else has talked about. Because the gap between what the technical literature is saying and what the public conversation knows is exactly the kind of gap where civilization-scale risks live, and the gap closes either because the public eventually finds out or because the event arrives and closes the gap for us. We would rather close it the first way, but there is one more layer to this picture. And it is the layer where the technical machinery of the prediction meets the operational machinery of what we are actually equipped to do about it. Number, Part 6. The framework gap. Operational space weather management in the United States is the responsibility of the Space Weather Prediction Center, a small office within the National Oceanic and Atmospheric Administration based in Boulder, Colorado. The center operates 24 hours a day. It issues forecasts, warnings, and watches for solar flare activity, geomagnetic storms, and radiation events. Its products are used by grid operators, satellite operators, aviation authorities, the military, and an increasing number of commercial enterprises whose operations depend on space-based infrastructure. The Space Weather Prediction Center is well-staffed and competently led. The people who work there are excellent. The institutional mission is sound. The framework gap is not a personnel problem. The framework gap is that the center's operational products, by design, exist on a scale that does not extend into the S-class regime. The 5-level G scale for geomagnetic storms tops out at G5. The 5-level R scale for radio blackouts tops out at R5. The 5-level scale for solar radiation storms tops out at S5. These scales were designed during the period of continuous instrumental observation, calibrated against the events that the instrumental record contains, and built to communicate threats that fall within the range of human experience. What happens when an event arrives that exceeds the top of the scale? The procedural answer is that the center issues the highest level warning available and continues to issue updates as the event develops. That is what would happen. The scale would, in effect, simply max out. The G5 warning that was issued for the May 2024 storm is the same warning that would be issued for an event 10 times larger. The operational vocabulary does not have a way to communicate the difference. The infrastructure operators who receive the warning would not, from the warning alone, know whether they were about to absorb a manageable event or an event that exceeds the design parameters of every piece of equipment they own. This is not a criticism of the Space Weather Prediction Center. It is a description of the system we have. The scales were not designed to cover events at the upper end of what the historical cosmogenic record suggests is possible, because the scales were designed before we had the cosmogenic record, and because operational forecasting has always centered on the events that have actually happened during the instrumental era. The Velasco-Herrera paper is, in part, a request that the field expand its operational scales to accommodate the S-class regime. The paper proposes a probabilistic spatiotemporal forecasting framework that identifies windows of elevated risk for events above X10. That is, in operational terms, a step toward closing the framework gap. It is a small step. It is the first step. The next steps require institutional adoption, integration into operational products, and translation into communication channels that grid operators and satellite operators and the general public can actually use. That process is slow. The Space Weather Prediction Center moves carefully because the consequences of crying wolf are real, and the consequences of premature public alarm in a probabilistic threat domain are also real. The center has not adopted S-class as an operational category. The standard scales remain in place. The forecast products distributed daily continue to use the existing vocabulary. The Velasco-Herrera framework exists in the academic literature, not in the operational warnings that grid operators receive. This means that during the 18-month window the paper has identified, the operational warnings that are issued will look like the operational warnings that have always been issued. The X-class probability forecasts will be elevated. The geomagnetic storm warnings will be issued at the standard G-scale levels. The communication that goes out to the public, when it goes out at all, will be the communication that has always gone out, framed by the scales that have always been used. The gap is the gap between what the new research is saying and what the operational infrastructure is communicating. The gap is not malicious. It is procedural. It is what happens when scientific understanding moves faster than operational adoption, which is a recurring pattern in every applied science field, but which has consequences in this field that are larger than usual. Now consider the receiving side of the operational framework: the grid operators, the satellite operators, the aviation authorities, the cellular network managers. Grid operators in North America operate under standards set by the North American Electric Reliability Corporation, which has, over the last 15 years, gradually incorporated geomagnetic disturbance into its planning standards. The standards require grid operators to assess the vulnerability of their systems to geomagnetic events, to model the induced currents that a benchmark event would produce, and to implement mitigation measures where the modeled exposure exceeds defined thresholds. The benchmark event used by the North American Electric Reliability Corporation is a 1 in 100-year storm, defined in terms of geoelectric field strength at specific latitudes. That benchmark is a step forward from where the industry was 20 years ago. It is also, almost certainly, an underestimate of what a Miyake-class event would produce. The benchmark is calibrated against the modern instrumental record, which does not contain a Miyake-class event. The grid is being assessed against a threat envelope that does not extend to the upper bound of the historical record. Satellite operators operate under standards that vary by operator and by satellite type. The major commercial operators have hardening standards, operational procedures, and contingency plans. The standards have been progressively improved as new threats are identified, but the standards are bounded by the same historical experience that bounds the grid standards. Hardening that is adequate for a G5 storm is not necessarily adequate for an event 5 times larger. The May 2024 storm was, in operational terms, a stress test that the satellite industry largely passed, with some losses that are now being incorporated into updated standards. A Miyake-class event would be a stress test of a different order, and the industry has not been tested at that level. Aviation authorities monitor space weather for impacts on high-frequency communication, on global positioning system navigation, and on radiation exposure on high-latitude routes. During major events, polar routes are diverted to lower latitudes where the radiation environment is less severe. The diversions add fuel cost and flight time but do not produce safety-critical impacts under typical event conditions. A Miyake-class event would produce radiation exposure on polar routes that is, by some estimates, an order of magnitude or more above the levels at which routine diversions are currently triggered. The procedural response would be ground stoppage on a broader scale than has ever been operationally implemented for a space weather event. The aviation industry has not practiced this scenario at scale. The framework gap is not in any single agency or any single industry. It is in the cumulative mismatch between the threat envelope that the literature describes and the threat envelope that the operational infrastructure has been designed against. The gap is roughly equivalent to the gap between the strongest hurricane on record and the strongest hurricane that climate physics says is possible. The infrastructure is built for the first envelope. The actual maximum threat is in the second. Stay with me. This is the part where the implications get specific. If a Miyake-class event occurs during the predicted 18-month window, the operational response will be initiated by the warning systems that exist today, using the scales and vocabulary that exist today, communicated to operators who have prepared against threat envelopes that exist today. The response will be competent. The personnel are excellent. The procedures are sound. The procedures were designed for events smaller than the one being responded to. The likely consequence is that mitigation measures that would have been sufficient against a G5 event will be insufficient against the event in progress. Transformers that would have stayed online during May 2024 will saturate and fail. Satellites that would have rebooted and resumed operations will instead suffer permanent damage. Power outages that would have lasted hours will last weeks or months. The global positioning system constellation, which has redundancy designed against the failure of small numbers of satellites, will experience failures larger than the redundancy was designed for. The cascading effects are where the framework gap actually translates into damage. The grid going down takes communications networks with it after backup power runs out. Communications networks going down disable coordination of emergency response. Lack of coordination delays repairs. Delayed repairs extend outages. Extended outages disable water treatment, fuel distribution, food supply, medical services, financial settlement, and the supply chain dependencies that those services rely on. Each layer of failure makes the next layer of failure worse. The system does not have a graceful degradation mode for an event of this magnitude. The system has not been designed with one because the design parameters did not include this magnitude. That is, the framework gap. The space between what the science says is possible and what the engineering has been built to withstand. Let us be specific for a moment about what transformer replacement actually looks like, because this is the bottleneck that determines whether a recovery takes weeks or years. An extra high voltage transformer is a custom-built piece of equipment, typically weighing between 200 and 500 tons, with dimensions on the order of a small house. The transformer contains a magnetic core of laminated electrical steel, primary and secondary windings of insulated copper, and a tank filled with mineral oil that serves both as electrical insulation and as a coolant. The construction is precise. The tolerances are tight. The materials are specialized. The manufacturing process for a single unit takes between 12 and 20 months from initial order to delivery. Global manufacturing capacity for extra high-voltage transformers is concentrated in a small number of specialist plants. The largest manufacturers are in South Korea, in Germany, in India, in China, and in the United States. Although the United States production capacity has declined significantly over the last several decades and now accounts for only a small fraction of the units installed in the North American grid, the remaining North American grid transformers are sourced largely from foreign manufacturers, with the longest lead times coming from the most specialized units, serving the highest voltage transmission classes. In a normal year, the global production capacity for the highest voltage classes is, by various industry estimates, in the range of 200 to 300 units. The demand for replacements in a normal year is roughly matched to that production, with utilities planning ahead for known retirement and expansion needs. There is essentially no slack capacity. There is no surge production capability that can be rapidly activated. In the aftermath of a Carrington-class event with significant transformer damage in North America, the demand for replacements would, by the Lloyd's estimates, exceed annual global production capacity by a factor of several. The Lloyd's model assumes that between 300 and over 1,000 extra high-voltage transformers could be damaged or destroyed in a worst-case scenario. The replacement supply chain would not be capable of meeting that demand within any reasonable operational timeframe. The bottleneck would not be money. The bottleneck would be physical manufacturing capacity. This is why the high estimate of the Lloyd's outage duration extends to 1 to 2 years. The mathematics of the replacement supply chain do not permit faster recovery. Spare transformer inventories exist at major utilities, but the inventories are designed for routine failures, not for fleet-scale catastrophic damage. Mobile transformer units exist for emergency restoration, but the units are limited in number and are designed for lower voltage applications than the units most at risk from geomagnetic induction. The transformer story is one specific example of the framework gap. The same pattern applies to other critical components. Specialized integrated circuits in satellite electronics, replacement satellite manufacturing, the specific copper conductors and insulating materials used in high-voltage transmission, the pumping stations in fuel distribution networks, the control systems in water treatment plants. Each system has its own version of the replacement supply chain bottleneck. Each system has been designed for routine maintenance, not for civilization-scale catastrophic damage. The Quebec experience in March 1989 is instructive on this point. The Hydro-Quebec grid collapsed in approximately 90 seconds when one critical relay misoperated during the geomagnetically induced current event. The relay was protecting equipment from damage. The relay did exactly what it was designed to do. The consequence was that the protection cascaded across the network and the entire grid went down. 6 million customers lost power. Restoration took 9 hours, which is fast by the standards of major grid events, because the equipment damage was relatively limited and because the operators were able to bring the grid back up in stages. What the Quebec event also produced, and what is less widely reported, was permanent damage to a single transformer at the Salem nuclear power plant in New Jersey. The transformer was a generator step-up unit, the kind of transformer that connects the output of a power plant to the high-voltage transmission grid. It overheated during the storm, experienced internal failures, and required complete replacement. The replacement took months. During the replacement period, the Salem plant operated at reduced capacity. The cost of the replacement, including the lost generation revenue, was in the tens of millions of dollars. That was a single transformer. From a single storm, at a single location. The 1989 storm was, by the standards of what Cycle 25 has just demonstrated and what the new research is now warning about, a modest event. It cost one transformer at a nuclear plant, a Miyake-class event, with global distribution of induced currents across the high-latitude infrastructure, would cost orders of magnitude more transformers across orders of magnitude more locations, with replacement supply chains that have not been scaled to the demand. This is the actual operational picture, not a hypothetical, a direct extrapolation from the response curve that the existing infrastructure has demonstrated against events well below the threshold the next 18 months may bring. The gap is closable, in principle. Hardening can be improved, redundancy can be added, supply chains for replacement equipment can be diversified, operational procedures can be updated. The cost of doing these things, distributed across the various industries and agencies involved, is significant but not unmanageable. The cost of not doing them, if a Miyake-class event arrives within the window, is several orders of magnitude larger. The choice between those costs has not been made yet, because the conversation about making the choice has not really started. This is one of the things that Crisis Horizon Labs is trying to do with this briefing. To start the conversation, to put the framework gap in front of an audience that is large enough that the conversation can begin to move outside the technical journals where it has been confined. The conversation needs to move. The window is open. Number. Part 7. The convergence. We have walked through 5 layers of the problem. The anomaly in the solar magnetic state. The world beneath us that depends on electricity in ways most people never think about. The machinery of magnetic reconnection that produces flares and the timing of how their effects arrive. The nameless category of solar events that exist in the historical record but not in our operational vocabulary. The coverage gap that keeps this story buried even as the prediction window opens, and the framework gap between what the science says and what the infrastructure can absorb. Now, consider what it means that all of these layers are converging at the same moment. This is what nonlinear risk looks like. Not 5 independent problems that we manage in sequence. 5 intersecting problems that compound when they overlap. The solar anomaly is happening during the era in which we have the most space-based infrastructure ever deployed. The infrastructure is exposed in ways that scale with the deployment, not in ways that scale linearly. The forecasting capability has improved, but the limits of forecasting have not changed in the way that the deployment of infrastructure has changed. The historical record warns us about events the operational scales do not cover. The events the operational scales do not cover are the events the new paper says are now elevated in probability. And the conversation that would prepare the public for these events is not happening at the volume the situation requires. This is the part of the briefing where we have to sit with the asymmetry of what we are looking at. Not because we are trying to alarm anyone for the sake of alarm, but because the asymmetry is real, and pretending it is not real has costs that are larger than the costs of acknowledging it. The asymmetry is this. The probability of a Miyake-class event occurring in any given year is small. The standard estimate is on the order of 1 in 1,000 to 1 in 2,000. That is a rare event by any reasonable definition. Most years, including most years in the next 18 months, will pass without one. The base rate is low. But the probability has been adjusted upward by the Velasco-Herrera framework. Not from 1 in 1,000 to a near certainty. From 1 in 1,000 to something more like 1 in 50 or 1 in 100. During this specific window, in a specific solar hemisphere, with a specific class of event, the adjustment is statistically significant. It is also, by the standards of how civil society responds to elevated risk, modest. We have not been good at responding to threats whose annual probability sits in the 1 in 50 range. We do better at threats that are imminent and certain. We do worse at threats that are elevated but probabilistic. The cost asymmetry compounds this. The cost of a Miyake-class event with full infrastructure exposure is, in conservative estimates, in the trillions of dollars. The cost of meaningful preparation, distributed across the various industries and agencies involved, is in the tens of billions. The expected value calculation, even with the modest probability adjustment, strongly favors preparation. The political and institutional dynamics that determine whether preparation actually happens do not run on expected value calculations. They run on visible immediacy and political incentive. The visible immediacy is low. The political incentive is, at present, low. The situation will remain in this state until either the event occurs or the public conversation reaches a volume sufficient to shift the political incentive structure. This is the convergence point. We have a real threat. We have a forecasting framework that identifies the threat with statistical precision. We have an infrastructure that is not adequately prepared for the threat. We have a public conversation that has not been activated, and we have a window, defined by the science, during which the convergence is most acute. The window is roughly 18 months. We are at the beginning of it. Is this a coincidence or something else? Let me know in the comments. The question is not rhetorical. It matters whether the framework gap is closing during the window or staying open through it. The answer to that question depends on whether the conversation that should be happening starts happening. And the conversation starts where it has always started, which is with the people who have read the literature, who have thought through the implications, and who are willing to ask their own institutions hard questions about what the preparation actually looks like. The institutions can be asked. The questions are not exotic. What is the current vulnerability assessment of the regional grid to a 1 in 500-year geomagnetic event? What is the current spare transformer inventory and the projected replacement timeline if multiple units fail simultaneously? What is the current satellite hardening standard relative to a Miyake-class event? What is the current contingency plan for a global positioning system outage lasting weeks to months? What is the current public communication protocol for a space weather event that exceeds the existing operational scales? These are reasonable questions. They have answers. The answers are, in most cases, not what the asking public would like the answers to be. But the questions need to be asked, and the answers need to be heard. And the next set of decisions about preparation needs to be made on the basis of those answers, rather than on the basis of the assumption that the threat is not in the room. The threat is in the room. It has been since the Velasco Herrera paper was published. It will remain in the room until the window closes or until the event arrives. There is one more thing to say about the convergence, and it is the thing that makes solar weather different from most of the other categories of threat we cover at Crisis Horizon Labs. Solar weather is a threat that has nothing personal about it. It is not the result of policy failure. It is not the result of corporate negligence. It is not the result of geopolitical conflict. It is not the result of climate change, although the broader question of how anthropogenic climate change interacts with the upper atmosphere during major events is a real and underexplored question. Solar weather is, simply, the behavior of the star our planet orbits. The star is doing what stars of its type do. The fact that we are exposed to that behavior is a consequence of having built our civilization on a planet that happens to be situated where it is, in the inner heliosphere of a sun-like star, during the technological era when our infrastructure has become capable of being affected by what the star does. It is the most cosmic of natural hazards. It is also, in some ways, the most banal. The sun is just going to do what the sun does. We have no recourse to influence the sun's behavior. The only recourse we have is to harden what we have built against what the sun is going to do, and to communicate clearly with each other about what we are exposed to. We have not been doing those things at the level the situation requires. The window has opened. The conversation is now. Number. Conclusion. I want to bring this back to the people I named at the beginning. The 1.2 billion people across the high latitudes of the Northern Hemisphere who are about to spend the next 18 months living downstream of an anomaly in the Southern Hemisphere of the Sun without knowing they are doing it. They are not in a hurricane path. They are not in an earthquake zone. They are not living above an active volcano or downstream of a failing dam. They are living in cities and towns and rural communities at latitudes where their grids are most exposed to geomagnetically induced currents, and where their satellite-dependent services are exposed to the same particle environment that exposes everyone else. They are going about their lives. They are working. They are raising children. They are planning vacations and saving for retirements and worrying about the things that ordinary life gives people to worry about. They are not worrying about this. Almost none of them are. They have not been told to. The story has not reached them. The operational warnings will not reach them until the event arrives, if it arrives. The framework that would prepare them is the framework gap we have been describing. This is not their fault. They cannot be expected to read peer-reviewed solar physics papers in their spare time. They cannot be expected to track the operational products of the Space Weather Prediction Center on a daily basis. They are doing what people in functioning societies do, which is trust that the infrastructure they depend on has been designed and maintained against the threats that are foreseeable. They are not, in any way, irrational to trust that. The infrastructure has been designed against many threats. The threat we have been describing tonight is one of the threats it has not been adequately designed against. That is the gap. That is the cost of the coverage gap and the framework gap layered on top of the actual solar anomaly the science has identified. The real story tonight is not that the sun is about to produce a superflare. The real story is that we have built a civilization whose continuity depends on the sun, continuing to behave the way it has behaved for 70 years of monitored history. Even though we have direct evidence that the sun is capable of behaving differently, and even though the latest research is telling us the probability of different behavior has just elevated, the real story is the distance between what the science knows and what the public is doing about it. That distance closes either through preparation or through impact. Preparation is the slow, expensive, politically difficult work of upgrading hardening standards, expanding redundancy, diversifying supply chains, updating operational scales, and changing the way the public conversation about solar weather is conducted. Impact is the fast, expensive, civilizationally traumatic work of absorbing an event the infrastructure was not ready for and then rebuilding what failed. We have a choice between those two paths. The choice is not made by any single individual or institution. It is made by the cumulative decisions of the operators and the regulators and the legislators and the journalists and the public who collectively determine which work gets done before the window closes. The decisions are being made, and not made, every day. The window is open. In the meantime, the southern hemisphere of the sun continues to do what it has been doing. Active regions on the far side, currently hidden from direct observation, continue to develop. They will rotate into Earth-facing geometry within days. The sun has not announced what it is going to do. The sun, in all probability, does not yet know what it is going to do. The reconnection threshold has not yet been crossed in any of the magnetic configurations that are building. The triggering perturbation has not yet occurred. The event, if it occurs, is in the future tense. But the conditions for it are in the present tense, and the people who will be downstream of it are in the present tense. And the choice about whether to prepare for it is in the present tense. That is where we leave it tonight. Take a moment, before you scroll on, to think about who in your life depends on infrastructure that runs on electricity and on satellite-dependent services. That is, statistically, almost everyone. Think about what a multi-week disruption to that infrastructure would look like for them. Think about what conversations you would want to have had with them. What preparations you would have wanted to make if the window closed not through preparation but through impact. The conversation does not have to start at the level of preparing for a Carrington-class event. It can start at the level of asking your local utility what their geomagnetic disturbance assessment looks like. It can start at the level of asking your representatives what the space weather appropriation looks like in the current budget cycle. It can start at the level of having read this briefing and shared it with one person who has not yet thought about any of this. The window is roughly 18 months. We are at the beginning of it. The southern hemisphere of the sun is anomalous. The framework gap is open. The coverage gap is wide. The people on the receiving end are doing their lives. The sun is doing whatever the sun is doing. We are not going to pretend that we know which way this resolves. We are going to tell you that the prediction window has been published. The science is real. The infrastructure is exposed, and the conversation needs to start moving faster than it has been moving. This is Crisis Horizon Labs. We will be tracking this through the duration of the window. If there is an event, we will be here covering it. If there is no event, we will be here documenting what changed during the window and what did not. Either way, the story is going to continue. Tell us in the comments what you would want to know more about. What infrastructure question keeps you up at night? What gap in the coverage you would want us to close next? The next briefing in this series will examine the specific transformer vulnerability question in greater technical detail, including what the actual replacement supply chain looks like and where the bottlenecks would emerge under a multi-component failure scenario. It is a story that almost nobody is telling and that, in the 18 months we have just opened, almost everyone needs to understand. Subscribe if you have not. Share this with one person who has not yet considered solar weather as a personal risk category. And whatever else you do, do not look away from the Sunday. It has been a long time since the sun did the thing it is now statistically positioned to do. The time is closing. Stay safe.